In physics, sound is a vibration that propagates as a typically audible mechanical wave of pressure and displacement through a medium such as air or water. In physiology and psychology, sound is the reception of such waves and the perception by the brain. Acoustics. Acoustics is the interdisciplinary science that deals with the study of mechanical waves in gases, liquids, and solids, including vibration, sound, ultrasound, and infrasound. A scientist who works in the field of acoustics is an acoustician, while someone working in the field of acoustical engineering may be called an acoustical engineer. An audio engineer, on the other hand, is concerned with the recording, manipulation, mixing, and reproduction of sound. Applications of acoustics are found in almost all aspects of modern society. Subdisciplines include aeroacoustics, audio signal processing, architectural acoustics, bioacoustics, electroacoustics, environmental noise, musical acoustics, noise control, psychoacoustics, speech, ultrasound, underwater acoustics, and vibration. Definition. Sound is defined by ANSI, ASHA S1.1-2013 as oscillation in pressure, stress, particle displacement, particle velocity, etc., propagated in a medium with internal forces, or the superposition of such propagated oscillation. Auditory sensation evoked by the oscillation described in Physics of Sound. Sound can propagate through compressible media such as air, water and solids as longitudinal waves and also as transverse waves in solids. The sound waves are generated by a sound source, such as the vibrating diaphragm of a stereo speaker. The sound source creates vibrations in the surrounding medium. As the source continues to vibrate the medium, the vibrations propagate away from the source at the speed of sound, thus forming the sound wave. At a fixed distance from the source, the pressure, velocity, and displacement of the medium vary in time. At an instant in time, the pressure, velocity, and displacement vary in space. Note that the particles of the medium do not travel with the sound wave. This is intuitively obvious for a solid, and the same is true for liquids and gases. During propagation, waves can be reflected, refracted, or attenuated by the medium. The behavior of sound propagation is generally affected by three things: a complex relationship between the density and pressure of the medium. This relationship, affected by temperature, determines the speed of sound within the medium. Motion of the medium itself. If the medium is moving, this movement may increase or decrease the absolute speed of the sound wave depending on the direction of the movement. For example, sound moving through wind will have its speed of propagation increased by the speed of the wind if the sound and wind are moving in the same direction. If the sound and wind are moving in opposite directions, the speed of the sound wave will be decreased by the speed of the wind. The viscosity of the medium. Medium viscosity determines the rate at which sound is attenuated. For many media, such as air or water, attenuation due to viscosity is negligible. When sound is moving through a medium that does not have constant physical properties, it may be refracted. The mechanical vibrations that can be interpreted as sound are able to travel through all forms of matter, gases, liquids, solids, and plasmas. The matter that supports the sound is called the medium. Sound cannot travel through a vacuum. Longitudinal and transverse waves. Sound is transmitted through gases, plasma, and liquids as longitudinal waves, also called compression waves. It requires a medium to propagate. Through solids, however, it can be transmitted as both longitudinal waves and transverse waves. Longitudinal sound waves are waves of alternating pressure deviations from the equilibrium pressure, causing local regions of compression and rarefaction, while transverse waves are waves of alternating shear stress at right angle to the direction of propagation. Sound waves may be viewed using parabolic mirrors and objects that produce sound. The energy carried by an oscillating sound wave converts back and forth between the potential energy of the extra compression or lateral displacement strain of the matter and the kinetic energy of the displacement velocity of particles of the medium. Sound wave properties and characteristics. Although there are many complexities relating to the transmission of sounds at the point of reception, sound is readily dividable into two simple elements: pressure and time. These fundamental elements form the basis of all sound waves. They can be used to describe, in absolute terms, every sound we hear. Figure 1 shows a pressure over time graph of a 20 milliseconds recording of a clarinet tone. However, in order to understand the sound more fully, a complex wave such as this is usually separated into its component parts, which are a combination of various sound wave frequencies. Figure 2 shows an example of a series of component sound waves such as might be seen if the clarinet sound wave was broken down into its component sine waves, but with the lower frequency components removed. Sound waves are often simplified to a description in terms of sinusoidal plane waves, which are characterized by these generic properties: frequency, or its inverse, the wavelength, amplitude, sound pressure, intensity, speed of sound, direction. Sound that is perceptible by humans has frequencies from about 20 Hz to 20,000 Hz. In air at standard temperature and pressure, the corresponding wavelengths of sound waves range from 17 meters to 17 millimeters. Sometimes speed and direction are combined as a velocity vector. Wave number and direction are combined as a wave vector. Transverse waves, also known as shear waves, have the additional property, polarization, and are not a characteristic of sound waves. Speed of sound. The speed of sound depends on the medium that the waves pass through, and is a fundamental property of the material. The first significant effort towards the measure of the speed of sound was made by Newton. He believed that the speed of sound in a particular substance was equal to the square root of the pressure acting on it divided by its density. This was later proven wrong when found to incorrectly derive the speed. French mathematician Laplace corrected the formula by deducing that the phenomenon of sound traveling is not isothermal, as believed by Newton, but adiabatic. He added another factor to the equation gamma and multiplied 2, thus coming up with the equation. Since the final equation came up to be, which is also known as the Newton-Laplace equation. In this equation, K equals elastic bulk modulus, C equals velocity of sound, and equals density. Thus, the speed of sound is proportional to the square root of the ratio of the bulk modulus of the medium to its density. Those physical properties and the speed of sound change with ambient conditions. For example, the speed of sound in gases depends on temperature. In 20 degrees Celsius air at sea level, the speed of sound is approximately 343 meters per second using the formula V equals meter per second. In fresh water, also at 20 degrees Celsius, the speed of sound is approximately 1,482 meters per second. In steel, the speed of sound is about 5,960 meters per second. The speed of sound is also slightly sensitive to the sound amplitude, which means that there are nonlinear propagation effects, such as the production of harmonics and mixed tones not present in the original sound. Perception of sound. A distinct use of the term sound from its use in physics is that in physiology and psychology, where the term refers to the subject of perception by the brain. The field of psychoacoustics is dedicated to such studies. Historically, the word sound referred exclusively to an effect in the mind. Webster's 1947 dictionary defined sound as that which is heard, the effect which is produced by the vibration of a body affecting the ear. This meant the correct response to the question, if a tree falls in the forest with no one to hear it fall, does it make a sound, was no. However, owing to contemporary usage, definitions of sound as a physical effect are prevalent in most dictionaries. Consequently, the answer to the same question is now, yes. A tree falling in the forest with no one to hear it fall does make a sound. The physical reception of sound in any hearing organism is limited to a range of frequencies. Humans normally hear sound frequencies between approximately 20 Hz and 20,000 Hz. 382. The upper limit decreases with age. Sometimes sound refers to only those vibrations with frequencies that are within the hearing range for humans, or sometimes it relates to a particular animal. Other species have different ranges of hearing. For example, dogs can perceive vibrations higher than 20 kHz, but are deaf below 40 Hz. As a signal perceived by one of the major senses, sound is used by many species for detecting danger, navigation, predation, and communication. Earth's atmosphere, water, and virtually any physical phenomenon, such as fire, rain, wind, surf, or earthquake, produces its unique sounds. Many species, such as frogs, birds, marine and terrestrial mammals, have also developed special organs to produce sound. In some species, these produce song and speech. Furthermore, humans have developed culture and technology that allows them to generate, record, transmit, and broadcast sound. Elements of sound perception. There are 6 experimentally separable ways in which sound waves are analyzed. They are pitch, duration, loudness, timbre, sonic texture, and spatial location. Pitch is perceived as how low or high a sound is and represents the cyclic, repetitive nature of the vibrations that make up sound. For simple sounds, pitch relates to the frequency of the slowest vibration in the sound. In the case of complex sounds, pitch perception can vary. Sometimes individuals identify different pitches for the same sound, based on their personal experience of particular sound patterns. Selection of a particular pitch is determined by pre-conscious examination of vibrations, including their frequencies and the balance between them. Specific attention is given to recognizing potential harmonics. Every sound is placed on a pitch continuum from low to high. For example, white noise sounds higher in pitch than pink noise, as white noise has more high-frequency content. Figure 1 shows an example of pitch recognition. During the listening process, each sound is analyzed for a repeating pattern and the results forwarded to the auditory cortex as a single pitch of a certain height and chroma. Duration is perceived as how long or short a sound is and relates to onset and offset signals created by nerve responses to sounds. The duration of a sound usually lasts from the time the sound is first noticed until the sound is identified as having changed or ceased. Sometimes this is not directly related to the physical duration of a sound. For example, in a noisy environment, gapped sounds can sound as if they are continuous because the offset messages are missed owing to disruptions from noises in the same general bandwidth. This can be of great benefit in understanding distorted messages such as radio signals that suffer from interference, as the message is heard as if it was continuous. Figure 2 gives an example of duration identification. When a new sound is noticed, a sound onset message is sent to the auditory cortex. When the repeating pattern is missed, a sound offset message is sent. Loudness is perceived as how loud or soft a sound is and relates to the total number of auditory nerve stimulations over short cyclic time periods, most likely over the duration of theta wave cycles. This means that at short durations, a very short sound can sound softer than a longer sound even though they are presented at the same intensity level. Past around 200 milliseconds, this is no longer the case and the duration of the sound no longer affects the apparent loudness of the sound. Figure 3 gives an impression of how loudness information is summed over a period of about 200 milliseconds before being sent to the auditory cortex. Louder signals create a greater push on the basilar membrane and thus stimulate more nerves, creating a stronger loudness signal. A more complex signal also creates more nerve firings and so sounds louder than a simpler sound, such as a sine wave. Timbre is perceived as the quality of different sounds and represents the pre-conscious allocation of a sonic identity to a sound. This identity is based on information gained from frequency transients, noisiness, unsteadiness, perceived pitch and the spread and intensity of overtones in the sound over an extended time frame. The way a sound changes over time provides most of the information for timbre identification. Even though a small section of the waveform from each instrument looks very similar, differences in changes over time between the clarinet and the piano are evident in both loudness and harmonic content. Less noticeable are the different noises heard, such as air hisses for the clarinet and hammer strikes for the piano. Sonic texture relates to the number of sound sources and the interaction between them. The word texture, in this context, relates to the cognitive separation of auditory objects. In music, texture is often referred to as the difference between unison, polyphony and homophony. But it can also relate to a busy cafe, a sound which might be referred to as cacophony. However, texture refers to more than this. The texture of an orchestral piece is very different to the texture of a brass quartet because of the different numbers of players. The texture of a marketplace is very different to a school hall because of the differences in the various sound sources. Spatial location represents the cognitive placement of a sound in an environmental context, including the placement of a sound on both the horizontal and vertical plane, the distance from the sound source and the characteristics of the sonic environment. In a thick texture, it is possible to identify multiple sound sources using a combination of spatial location and timbre identification. It is the main reason why we can pick the sound of an oboe in an orchestra and the words of a single person at a cocktail party. Noise is a term often used to refer to an unwanted sound. In science and engineering, noise is an undesirable component that obscures a wanted signal. However, in sound perception it can often be used to identify the source of a sound and is an important component of timbre perception. Soundscape is the component of the acoustic environment that can be perceived by humans. The acoustic environment is the combination of all sounds within a given area as modified by the environment. Sound pressure level. Sound pressure is the difference, in a given medium, between average local pressure and the pressure in the sound wave. A square of this difference is usually averaged over time in, or space, and a square root of this average provides a root mean square value. For example, 1 Pascal RMS sound pressure in atmospheric air implies that the actual pressure in the sound wave oscillates between that is between 101,323.6 and 101,326.4 pascals. As the human ear can detect sounds with a wide range of amplitudes, sound pressure is often measured as a level on a logarithmic decibel scale. The sound pressure level, or LP, is defined as where P is the root mean square sound pressure, and is a reference sound pressure. Commonly used reference sound pressures, defined in the standard ANSI S1.1-1994, are 20 micropascals in air and 1 micropascal in water. Without a specified reference sound pressure, a value expressed in decibels cannot represent a sound pressure level. Since the human ear does not have a flat spectral response, sound pressures are often frequency-weighted so that the measured level matches perceived levels more closely. The International Electrotechnical Commission has defined several weighting schemes. A weighting attempts to match the response of the human ear to noise, and A-weighted sound pressure levels are labeled dBA. C weighting is used to measure peak levels.